Alright, so the momentum equation. Right? Probably we have our introduction, derivation, deflectors and bend and propellers. Okay, so that's some of the what do you call it? Topics that we will discuss, and probably we can finish it today. Alright, so you see this? This is what we call uh turbine. Alright, part of these. Do you remember yesterday we have the example of example number one, where we generating an electricity, is it right? By using a turbine. So one type of the turbine is called the Pelton wheel. Okay, so this is a Pelton wheel. You see how huge is that? It's very big, right? This is very big, and but the basic principle of this turbine is that we have that turbine or that bucket there. All right, they call it bucket. You see the word bucket there. Okay, so this turbine doesn't rotate. All right, it doesn't move at all until we send a jet of a jet of fluid, all right, into the what we call the bucket itself. Okay, so because of this a high speed jet, all right, striking the bucket, so the whole pattern wheel will start to rotate. Okay, so from that rotation, then we take the energy from that mechanical rotation, and then we change it into the electricity. Okay, so that's how it works in real life. Okay, this is a real life story. Yeah? Not a just picture, but a real life story. Okay, so the question is, when we draw the bucket there, or when we design that bucket, so we want to make sure that the angle is correct. All right, the angle is correct, and then I mean the speed of the jet coming out from that nozzle tracking the wheel must also correct. All right, in order to create, for example, yesterday we have what 810 gigawatt or something like that. Okay, that yesterday example. Okay, so now you see this is in detail now. All right, this is in detail. We need to strike that bucket in order for that bucket to rotate, and finally create the what we call the electricity. Okay, so we will learn all of this. Okay, and it said learning outcome for this particular topic is that use Newton's second law of motion to develop the force equation, or we call it the momentum equation. Okay, so we use the Newton's second law. Okay, and then after completing this chapter or this topic, you should be able, all right, to use the momentum equation to compute the force exerted on a stationary object that causes the change in direction of the flow stream. Okay, you should be able to, okay, you should be able to, all right, to use that momentum equation and analyze that. Use the momentum equation to compute the force exerted on a band in pipeline. Okay, so you need to know the band. Use momentum equation to compute the force on a moving object. So sometimes you have a static object, all right, where we have a jet of fluid striking a static object, and sometimes we have a moving target. All right, a moving target. We call it a moving target. Okay, so let's start with, okay, start with the Reynolds transport theorem equation. All right, because why? Because remember when I said, okay, when the fluid start to move, there must be a mass moving, there must be energy, and there must be momentum. Okay, I think we already discussed that in order to determine the rate of change of these three, what we call extensive properties, which is a mass, energy, momentum. Okay, so we use what we call Reynolds transport theorems, or the simple word is we call what? control volume method. All right, control volume method. Okay, and if I'm not mistaken, all right, if I'm not mistaken, I think the textbook are using the dn over dt, all right? They use this dn over dt, but I'm here using, in the textbook, we are using dn over dt, just the same thing, all right? So this one, I'm using the dn over dt is equal to d dt integration control volume, and I'm using a b, a small b. Some textbook are using beta, and our textbook are using eta, the end with the leg or with the tail, all right, and rho d volume plus the integration at the control surface b rho b dot da. Okay, so what is meaning of this equation? All right, where b is an extensive properties proportional to a mass, while the small b is the corresponding intensive properties, all right, which been defined as the b, the extensive property, divide by mass. Okay, I hope you remember it when you see it, you say, oh, I remember that. Okay, I hope you remember that one. Okay, so next review. This is a review. Okay, we recall that the system, all right, which is the B, all right, this one, all right, the B system here, dB over dt here is a fluid volume that move along the fluid particle. So they move the whole fluid in the straight line, for example. And then the control volume, the CV, may move relative to the fluid. Sometimes the control volume is moving together with the fluid. Okay, sometimes. All right, but sometimes we say, okay, no, it just fix that. All right, the example I give you, or the definition of the control volume, I showed to you last week or last 2 week. All right, we have a fixed control volume. All right, but sometimes the control volume can move together. Okay, the example of moving together is, do you remember exercise 7? All right, where you have a tank, and then we have the small opening at the bottom, all right, and then the fluid is inside that what a reservoir, all right, or the tank. Okay, so your control volume is the surface, all right, through the whole amount of fluid inside that reservoir. Okay, so when the surface at the top, when the fluid is moving at the bottom, and then the surface at the top is moving together, so that's what I mean the control volume is moving relative to the fluid. It follow the fluid. Okay. The control surface is a closed surface that contain the control volume. This just a review, right? We already discussed this in detail, and most of you already understood it, right? How I know that? Because there are no question from you. So when there is no question, it means that everybody is happy and then they understand it. Okay, and then when somebody uh, asks you a question, you can answer it very fluently. All right. Okay, and then we have this, what is the A over here, all right? We have this dB over dt, we call it the term A. Over here, we call it as a B, and the last term here, we call it C. So what is the meaning of this? All right, term A describes the physical change that take place for the set of fluid particle. Okay, what's that? We want to know the rate of change of mass, rate of change of energy, and rate change of the momentum for the whole system. Okay, so the term B describes the change of observed in, all right, given control volume. Don't forget here, over here you see the control volume. All right, so the rate of change of what, of this intensive property inside the control volume. Okay, and then plus the term C describe the different. For example, if the property B has not changed for the fluid particle, but okay, so basically the D is what happened at the control surface. Okay, so the equation that we have in front of us now, we call it as the control volume equation for unsteady and non-uniform flow. Please remember that. Okay, this is for unsteady and non-uniform flow. Okay, next. And today, all right, now we have this linear momentum. You see that? All right, the linear momentum, fixed control volume. And today we use the momentum principle. We will do two things. All right, number one, use the law of conservation of momentum, which is the second law. And then set B, the capital B, as the M time V. M time V. Right? Because momentum is m time v, right? Mass time velocity. Okay, and substitute this into the Reynolds transport theorem equation. Let me see. Okay, we change this b here in terms of mb, m time v. So why you want to change that? Because today we want to know what is the rate of momentum change in the system. Okay, so that's why we change it into the m time v. Okay, all right, and then notice the similarity to the last lecture. Is it last lecture? Or whatever previous lecture there. Okay, where we use conservation of mass, the dm over dt is equal to 0, and we set the b is equal to b equal to m. So in this case, we set our b now become what? mv divided by m. So you have a small v. Okay. All right. So from Newton's second law, they said, okay, some force is equal to m times a, or we can say summation of force actually is equal to m, which is a mass, and a is the rate of change of velocity, right, which is dv over dt. While the definition of linear momentum, which is momentum, not our mom there, all right, momentum is equal to m times v, right? So conservation of momentum, then we said summation of force is equal to d mom, the momentum over dt. Okay, so conservation of momentum. The momentum observed in this system here, particle move about in the box, no particle leave or enter, hence the box is a system. So if you have something which is moving within a constrained compartment, all right, and no others were coming into it, or going out from that what do you call it, place there. So we call that as the conservation. We conserve it. All right. Thing is only happening inside it. So the whole thing inside it, we call it as a system. Okay. So particle can exchange momentum with each other, but does not affect the total momentum of the system. The only way to change the total momentum is to apply a force to the box. Okay. Okay. So therefore, all right. Therefore, we say okay, some dm over dt, we can put it as the sum of force is equal to the whole momentum divided by dt for the whole system. And then the Newton's second law of motion for a system is a time rate of change of the linear momentum of the system is equal to the sum of the external forces acting on the system. What this, sir? Never mind. I will explain it later. Okay, notice the similarity and the differences between conservation of mass and momentum. Okay, last time we said dm over dt for the whole system, the answer is equal to 0, right? We call it conservation of mass. Okay, but in this case, our d momentum over dt for the whole system, d is not equal to 0, but it is equal to summation of all forces. Okay, so dmv over dt for the whole system now is equal to what? Summation of the whole forces. When you sum the whole forces for the whole system, so that's what we call conservation of moment, conservation of momentum. Right? We see from this equation, both equations are applied to the system, all right? Both are applied to the system. Mass is conserved, absolutely. So there is no physical changes there, all right? So that's why we have this dm over dt is equal to 0. While the momentum is conserved unless the force is applied, all right? The momentum is conserved, all right, unless a force is applied, all right? Mass conservation is a scalar equation. Momentum conservation is a vector equation. So this over here we have what? Momentum, a vector. All right. Why the mass here? It is more a scalar. Okay, so Reynolds transfer theorem, which B equal to MV become dm over the whole system here. Okay, and then using the Newton's second law, we said this dm over dt here, dmv over dt here for the whole system actually is equal to what? Is equal to summation of the whole force. Okay, acting on that system. Okay, so we get the equation. We change the equation from this what we call the control volume equation, and we change it into our new equation here. We call it as the momentum equation. Okay, so the forces that act on the control volume are body forces and surface forces. The equation is vector equation. Momentum flow can be positive or negative. Out of the control volume, the time rate of change of momentum is 0 for the steady flow. So what are you doing today? Never mind, never mind. I will explain it later, okay? I just pass through all this slide and then I will explain it in detail in order for you to understand it much better compared to the one I just explained it here, right? Okay, so now, so we have this equation. The final equation for the momentum is equal to summation of force is equal to d over dt, integration control volume, v rho d volume, and then we have the control surface v rho v dot dA. All right, so notice that the little v and the big V in the last term. All right, we have a small v here, and we have this what the big V here, capital V. All right, so what is the difference? So the big V come from the Reynolds transfer equation, okay, which is in the equation, the original equation, while the V, the small or the little v, come from the momentum definition, okay. And then it is a fluid velocity relative to the reference frame. So this v here, the small or the little v here, is a velocity at that particular control surface. Okay, while this capital V here is what? Is the velocity for the whole system there. Okay, for the whole system. Okay,